So Kepler looks at 1/400th of the area of the sky. It looks at 100 square degrees. So if you put your hand out at arm's length, that's about 100 square degrees. And most of those stars that Kepler looks at are very far away. But if you take the planets that we've so far discovered and you do the statistics, you can calculate with fair confidence that there are probably more than 50 billion planets in our own galaxy, and maybe 500 million of those are habitable. So we've dreamed of other worlds for centuries. Right now, for the first time, they're a reality. And so for me, for my team, for the people at the SETI Institute, now is absolutely the perfect time to begin asking again the question, are we alone? So at the SETI Institute, we don't just do SETI. I have a very small team that works on SETI per se. The Institute has a very large cadre of astrobiologists who are interested in the origin, evolution, distribution, and future of life in the universe, any kind of life. So they study extremophiles here on Earth to understand the incredible range of conditions where life can thrive and flourish. That's not you and me, but it's life. And it is amazing the extremes that life can enjoy on this planet, and therefore, by inference, how much more real estate out there might be habitable. My colleagues are trying to find the answer to the question of what constitutes a biosignature. If you were able to image a terrestrial-like planet around a nearby star and study the chemistry of its atmosphere, is there any single smoking gun that would tell you for sure there's biology on the surface of that planet? Well, nature and real life isn't always as easy as smoking guns and for sures. There are some chemical signatures. We can look at our own atmosphere and see the presence of methane gas and molecular oxygen gas. And that's totally out of equilibrium. In the lab, if you put those two gases near one another, well, they're going to turn into carbon dioxide and water. And that's happening in our atmosphere all the time. But on the surface of the Earth, we have all these photosynthetic plants and trees that are producing oxygen. We have methanogens in the guts of termites in rice fields producing methane. We have that wonderful, ever-present bovine flatulence, cow fart producing methane. So biology is leaving an imprint on our atmosphere. And perhaps we can find something like that in the atmospheres of other planets, but it's very tricky to be able to say with absolute confidence that that particular chemical signature cannot be produced abiotically. So we're working hard on this, and perhaps a couple of decades from now we will have the wonderful space telescopes with the capable tools that are needed to do this trick. But what about in the meantime? What if there are mathematicians and engineers on those other worlds, and not just microbes? The SETI program is a scientific search to see if we can use the tools of the astronomer to detect technosignatures from out among the stars. Our own technologies are in fact visible at interstellar distances by an advanced technology. And perhaps their technology could be detected by us at radio or optical or some other wavelength if we only had a determined search to systematically look for it. Now, ultimately, whether or not we succeed in SETI is going to be determined by A, is there anybody else out there? And B, how long does their technology last? Because if technologies pop up out there in the galaxy, but they don't last for very long. And by very long, I mean in terms of cosmic timescales. Then there are never going to be any technological civilizations that are close enough in space and coexisting in time to detect one another. We are a very young technology, 100 years, in a very old galaxy whose age is 10 billion years, right? Can we become an old technology? Is technology, on average, a stabilizing influence? And do technologies last for a long time? Well, one of the ways to answer that question is to do SETI. Because Phil Morrison liked to point out, as a physicist at MIT, he liked to point out that SETI is the archaeology of the future. If we detect a signal, any information content in that signal will have traveled at the speed of light, but traveled over a long distance, so that information will actually be telling us about their past. But if we detect a signal, we understand that technologies can in fact last for a long time, so that we can look forward to a future.
Okay, imagine you're at the beach. In order to figure out if there are fish in the ocean, you dip an empty glass into the water and look inside. No fish in the glass? Well, there must be no fish in the ocean. Not too logical, is it?
No, not too logical. Nor is it logical to say, you guys have been searching for 50 years and haven't found anything. Must mean there's nothing out there. Well, 50 years is a short time in a cosmic time scale, and you have to understand that over that 50 years, we've not actually been on the telescope looking at the sky for very much of that, and our tools have not been optimized for the task. So in fact, if you consider the cosmic ocean, we've sampled about 1 glass of that ocean in 50 years. So that ocean still beckons us, and there's a really monumental task remaining to systematically search that ocean. But the 21st century offers us exponentially improving technologies to allow us to build bigger glasses and sample the ocean much more rapidly. So today we do SETI in 2 ways. We do optical SETI, and this is a search for optical wavelengths with telescopes, looking for bright pulses, bright flashes of light that last for a nanosecond, a billionth of a second or less. As far as we know, there's no kind of astrophysics that produces that kind of a signal. Yet our technology, our lasers, can do just that. So on the right, you see Shelley Wright when she was a senior at UC Santa Cruz, and this is the optical SETI detector she built for the Nichols telescope at Lick Observatory. On the left are a couple of Harvard students, and here is a full telescope that they've built to do an optical sky survey looking for these bright flashes. So optical SETI today is a kind of a university scale project. You use meter-class telescopes and instrumentation that isn't too difficult to build. It wasn't affordable before the start of the 21st century. 2000 was the first time we did optical SETI because the fast detectors were now affordable. And this kind of scale of instrumentation could detect the brightest of the most powerful lasers that we have on Earth today. Those are associated with the National Ignition Facility out in Livermore, right? these bright beams of lasers that are all concentrating their energy on this tiny little pellet to try and get it to fuse deuterium to helium and produce energy, fusion energy. But this kind of laser, this petawatt, 10 to the 15 watt laser, would be detectable by our optical setting programs if the laser was focused by a 10-meter telescope and was within 1,000 light years of Earth. Light year, that's the distance that light travels in a year, about 6 trillion miles. Our galaxy's 100,000 light years away, so this is 1% of the distance across our galaxy. That's what we can do today. There are millions of stars within that distance, and we're trying to study them to see if we can see an engineered signal at optical frequencies. We're also using the radio. So UC Berkeley continues to do SETI at home to allow people to download screensavers on their computers and analyze data that's been recorded at the Arecibo Observatory. And SETI at home did not invent distributed computing, but it was such a sexy application. People were so excited to be able to participate in SETI in any way that it really put distributed computing on the map. However, that's as far as it's gone. You install and you kind of forget about it. That's not good enough, right? I don't want your clicks, I don't want your CPU cycles, I don't want the electrons coming out of the wall to power your computer. I really want your think-ons. I want you to get involved in SETI. Because if you do, then maybe I can change your mind and your perspective on who you are, and maybe you can help me make our searches better. So in Northern California, we have built the first phase of a new radio telescope intended to do SETI all the time. It's also intended to do radio astronomy at the same time. There are 42 small antennas that are linked together with a whole lot of computing. And this is for the first time making silicon as important as aluminum and steel in constructing telescopes. And getting more capability in the future has two paths forward. We can build more telescopes for more sensitivity and collecting area, and then we can harness Moore's law to do more back-end signal processing and gain capability that way. And this idea of building a large telescope as a large number of small dishes is actually impacting the way that we will build telescopes in the future. So this is an artist's conception of what the Hat Creek Valley in Northern California will look like when we grow our antenna out to 350 telescopes. And here's an artist's impression of what the International Square Kilometer Array, the core of it might look like 2 decades from now, if it's ever built, either in the deserts of Western Australia or the deserts of South Africa and the Kalahari, in the deserts away from people and away from their technologies. And I think you can see the impact that this work we've done with the Allen Telescope Array is having already on the next generation of radio astronomy. So what could we see today? Well, the ATA could see not our television leakage. No, the power in those television and radio signals is so weak that we couldn't even see them to the nearest star. But if you consider the strongest transmitter on this planet, just as we talked about the strongest lasers that we have on our planet, that's a radar transmitter associated with the Large Radio Telescope in Puerto Rico. And its effective isotropic radiated power is 2 × 10 to the 13 watts. It's a lot, right? It's 2 megawatts of transmitted power with a gain of 10 to the 7 from that big collecting area, that radio telescope. And so we could see that if it were pointed at us and we're 1,000 light years away. So today we're looking for transmitters that are at the high end of what we ourselves can do. And we know that any technology out there, if it exists, is more advanced than we are. our technology is so young. We're an emerging technology. If there's technology out there, it's not going to be younger than ours. It will be older. And so today at the Allen Telescope Array, we're looking for signals in noise. We're looking for a particular kind of signal. Just as in the optical, we look for time compression, very short pulses. In the radio, we're looking for frequency compression. We're looking for something that shows up at one channel on the radio dial, one small region of the frequency space. Because nature doesn't do that. Nature spreads its power over lots of frequencies. So here's what we call a waterfall plot. Frequency runs horizontally, time runs vertically. Each of those little dots is a sample. Tells us how much power was detected at a particular frequency at a particular instant of time. And what you're looking at is the signal from the Voyager 1 spacecraft. It is the most distant human object. It is leaving the solar system and going into interstellar space. When these data were taken, it was 106 times as far away from us as we are from the sun. It's at the edge of our solar system. Have you seen the signal yet? It's there. Does that help? All right, that's what it looks like to our computer algorithms, because we've programmed them to find exactly that. Tell me any drifting straight line at any angle in that two-dimensional plane, and tell me how much power is it, and show me how it looks against statistical thresholds. So we do a great job at finding that kind of signal. All right, but what if we're not looking for the right kind of signal? What if there's a signal there that doesn't look like that? What if there's another pattern? So this is what, in 2009, I wished for when I was given an opportunity by the TED community to make a wish that could change the world. I wish that TED would empower Earthlings everywhere to become active participants in the ultimate search for cosmic company. How's this going to change the world? Well, actually, I think it can. I think it will. So here's a start. When you next log in, my next slide, when you next log in, go change the profiles that you have of yourself on Twitter, on LinkedIn, on Google+, on Facebook. And make the first thing that you say about yourself that you're an Earthling. And then join us as we try and build a global community to participate in this search and change the way we think of ourselves. Here's our first audience, right? University students. These folks are the first ones we're reaching out to because they're our future. They're going to be responsible for our technological longevity. They're going to solve the technical challenges that we've presented to them from technologies that we've previously produced and not used wisely. So we're looking for folks, we've published our code as open source. We're looking for folks who can build good code, make ours better, take what we have and do something else with it. We're looking for digital signal processing experts who can help us build algorithms to find signals that we don't yet detect. And for the rest of the world that aren't as smart as Harker School students or university students, don't have these technical skills, we'd like to build a citizen science application that allows humans to do what they do best, which is this pattern recognition. We want them to help us find things that we've missed, and we want them to help us work through parts of the spectrum that are so crowded with our own technologies that we have a hard time working through them. In the moment, we currently ignore them. So we're trying with SETI Quest, which is our community, to actively engage the world in this process. So what do? Well, we start with the telescopes. We've had lovely donations from Google and Dell and Intel of hardware, computing hardware. Amazon Web Services is supporting us to put a little of our data into the cloud so everyone can access it. We've published our code as open source. It's hosted by GitHub, and we're reaching out to those communities of students and digital signal processing experts who can help us with algorithm development. And this past summer, we had 2 students working with us on Google's Summer of Code. We're just starting on this citizen science application. We've worked with Francis Potter and the Hathersage group. So we have our first Android application, right, that's running on browser or tablet platforms. And it allows people to look through the data that's in the cloud, looking through lots of noise. This is early steps. It's in beta. We'd love to have you help us beta test it, but I gotta admit, it's pretty sucky. It's not real great yet. On the other hand, it's giving us very good data on which we can build with Galaxy Zoo a new citizen science project, which allows citizen scientists to work alongside with us in real time. They get a little bit of the data, they look through it, particularly these crowded bands where there are so many signals and we can't figure out what they are. We hope that they can help us work through this crowded part of the spectrum, and if they find something, that information comes back to the telescope and we instantly follow up on it, and they get to participate in the whole follow-up process. So here's a summary. We know where we want to point our array. We want to look at exoplanets. We've launched a 2-year program to explore the Kepler worlds, and we have a plan to involve Earthlings in the search. We're successfully building tools to engage the world and improve the search. Oops. What happened? Our partner in the Allen Telescope Array has been the University of California at Berkeley. They've helped us to innovate and build and operate this telescope. But the joint problems and pressures of federal budgets and California state budgets have made UC Berkeley have to put this telescope in hibernation as of the 15th of April and walk away from this project as our partner. So we've had to reach out to the world, who we want to involve anyway, and ask for support. We built a website called SETIstars.org, and we did a crowdfunding project. And within 45 days, we met a goal of $200,000, which is what we figure it will take us to bring this telescope out of hibernation once we have a new partner to operate it. And I'm really pleased to report that today my team's up there trying to get this array out of hibernation, trying to get it back working again. And we hope by the 25th of October that we're going to relaunch our search for Kepler worlds, and we'll start phases 2 and 3 of SETI Stars to keep the world involved, keep them supporting us, getting them involved in the search. And the reason that it's so important to get the world involved is because we've not really embraced this picture of where we live. Instead, we've seen millennia where you take a small island like this and you chop it up into even smaller islands. And then you fight one tribe against another. Well, it really, in the context of searching for extraterrestrial intelligence, makes no sense to think about ourselves as belonging to anything but a single tribe of Earthlings. I think SETI is so powerful because it can hold up a mirror that shows all of us an extraordinary perspective. We see ourselves in a different way when we think of ourselves in the context of looking for someone else out there. And I think that SETI can help us trivialize the differences among humans. And if it never does anything but reveal this perspective to all the humans on this planet, I think it will still have been among the most profound of endeavors that humans have ever undertaken. So please join us. That's the end of my time. And join in the search. And we'd love to have your help and your support. Thank you.